So looking at your notes, looks like you finished up your logarithmic differentiation. And then you talked about the inverse trig derivatives. He went through how to find them slightly differently than I went through how to find them. But ultimately, we end up with these lovely formulas. So the formulas are at the top. And once you have the formulas, doing the inverse trig derivatives are actually not that hard. What looks hard is when we're showing you where they come from. But in the end, you don't necessarily have to derive them every time. The ones that are super popular are the three that are over on this side. What you'll notice is that the three that are on the other side are exactly the same. They just have a minus sign in front of them. So they match up. The one for the inverse sine is the same as the one for the inverse cosine derivative. It's just the negative over there. And then same thing for a tangent versus cotangent, it's just the negative over there. So you really only have to memorize three of them and then memorize again the ones with the C's. Just like with our other derivatives, the ones with the C's have a negative on them. So it's not too hard to memorize them when you know that there's really only three of them there. Okay. So here's what I mean by once you have the formula, they don't actually suck all that much. If we're going to do the inverse tangent of e to the power of 2x, then what you want to do for your derivative is look up at our formula for inverse tangent, and it says we should do 1 over 1 plus whatever our x value is squared. Okay. The x value in this case is this e to the 2x. So I'm going to put the e to the 2x inside that set of parentheses there.
The 1 plus e to the 2x squared.
But I also need to multiply by the derivative. Yes. So you're still going to do your chain rule. So we need to still multiply by the derivative of this thing. So we're going to multiply by
e to the 2x.
So ultimately in our numerator, 2e to the 2x is up there. Down in the denominator, 1 plus e to the 4x. When you square that out. And you're done. That's it. So if you have the formula, it's not that bad. What he was showing you how to do today is where those formulas came from. But ultimately, we just got to know how to use them. So there's really three of them to memorize because all of these ones on this side that have C's, cosine, cotangent, and cosecant, they're just the negative of the ones over on this side. So there's really three formulas and then negatives to remember. The sine. If we want to do inverse sine of natural log of x's derivative, then we look up at our sine one. It's 1 over the square root of 1 minus whatever that x is squared. And then we have to do the chain rule. So our x value is the natural log of x. And then chain rule says take the derivative of the natural log of x, which is just 1 over x. So it's okay to leave it that way, or if you want, you can write it as x times the square root of 1 minus the natural log of x quantity squared. I have a couple in here with the secant because the secant formula looks scary because it's got the absolute value thing in there. It's not really that bad. We just keep the absolute value brackets in there if they matter. And then chain rule, we got to multiply by 5x to the 4th power. So totally fine to leave it like that. If we wanted to simplify it any, then you could go ahead and bring this and set it on top. You'd keep your absolute value brackets on the x to the 5th power because it actually matters because it's to a 5th power. If it were to a 4th power or it were squared, keeping the absolute value brackets on it wouldn't be necessary because things that are raised to a 4th power or to a 2nd power or 6th power, they're always going to come out to be positive. But something raised to the 5th power could still come out to be negative, so we need to leave them on there. Underneath, this could be x to the 10th power if you wanted, -1. You don't have to do that simplifying, but you can. So the same formula, 1 over our absolute value of the square root of x times the square root of the square root of x squared,
Which is
minus
just
1.
x.
And then we're going to multiply by the derivative of the square root of x. So if we remember that the square root of x is the same thing as x to the 1/2 power, then I want to do 1/2 x to the negative 1/2 power. In this case, the absolute value around the square root of x, we've just decided by convention is going to be the positive value. So you actually don't need to keep the absolute value sign if you don't want to there. And then this, the square root of x squared is just x. And then over here, if you want, you can write this as 1 over 2 times the square root of x, which means this one would actually simplify again if we wanted it to, as 1 over 2 times, because the square root of x and the square root of x will just become x here. It would be 1 over 2x times the square root of x minus 1. Totally fine to leave it like that, but it would simplify it more. So although these look kind of terrifying when we're going through and we're like, here's how you actually derive the formulas. Once you have the formulas, they're not really that bad. You're just plugging things in and then just not forgetting the chain rule part. That's kind of the thing that if someone's going to forget something, it'll be like, oh yeah, I got to chain rule that thing. Questions on any of those? Yeah.
For the first one,
Yeah.
You did 2e to the power of 2x.
Mm-hmm.
Why did it say 2x as the exponent?
So when I'm doing this part here for chain rule, if you take the derivative of e to the 2x, it's actually just e to the 2x, but then we have to take the derivative of the 2x part, and so that's where that 2 came from out front. So whenever you're doing an e to the something, so let's say it was like e to the 10x, if you took the derivative of e to the 10x, you still write e to the 10x times 10. Or if it was e to the pi x, you would do e to the pi x times pi. So whatever it is, because ours was e to the 2x, it's going to be e to the 2x times that 2 out front. Yeah. The e rule is write exactly what you see, and then chain rule the actual exponent part. The next part, I'm slightly ahead, but I think it's good to see it ahead of schedule. The related rates, you had a couple of practice problems on your midterm that used the related rates, and then he took them off and said, we didn't get there yet. They were the word problem ones. So if you took a look at those and you were like, what the heck? Related rates, that section has a lot to do with our implicit differentiation. So we had to learn implicit differentiation in order to do these types of problems, because we need to be able to take derivatives with respect to other variables.
I'm sorry, I'm just trying to figure out what.
Okay, so see, what I don't want you to do is try and go ahead of me because I haven't taught it yet. So hang on,
Okay.
Jen's gonna talk through it. It's not gonna be bad. Don't go ahead of me. It's not as bad as it looks. All right. I'm gonna read you, it's got 2 lines to it. Suppose the radius of a circle is increasing at a constant rate of 2 feet per second. How fast is the area changing when the radius is equal to 10 feet? We've already freaked out because there's words in there and there's geometry in there, right? Okay, so don't freak out. First thing Jen's gonna do is draw a circle. And for Jen, that's a pretty good circle. Most of my circles look very not round. That almost looks like a circle. Okay, now what I'm gonna do is remind you that the radius is from the center of the circle out to one edge. Diameter is when we go all the way across. This one's talking about just the radius. And so what they're saying is that this circle is actually getting bigger. The radius is increasing. And so as the radius is getting bigger, that means the circle is also getting bigger, right? The area of the circle gets larger as I make that radius bigger. What we wrote in here where it says that the radius is increasing at a rate of 2 feet per second, here's what you're going to write. dr over dt is equal to 2 feet per second. Okay, let's talk through why I wrote that. When we're talking about a rate is always something in terms of time. So that's why we have dt in the bottom. In terms of the variable that's getting bigger, they're telling us the radius is increasing. So that's why I put the dr in the top. So the radius is getting bigger with respect to our time changing. And they told us it's 2 feet per second. So that's where that came from. I didn't come up with anything. I'm just reading the words. That's going to be dr dt. The question is asking, how fast is the area changing? So they're asking you for a rate for the area. So what they want is the derivative of the area with respect to time, because they're asking about a rate. So that means it's always going to be dt if we're talking about a rate. We want dA dt specifically when r is equal to 10 feet. And so we're going to use this information to answer our question. So here's what I want. I want to write something about the area of a circle. Do you remember a formula for the area of a circle?
No.
Area equals
2 pi r squared.
ooh, you put
Pi r
2 of
squared.
them together. Yes. So 2 pi r is the circumference of the circle. That's 1. Area is pi times the radius squared. Nicely done. We want the area of the circle. But in order for me to answer the question, I don't want the area. I want dA dt. So here's where you're going to take your implicit differentiation skills. I want to differentiate this with respect to time. So what you're going to write is dA dt, because you're differentiating this formula with respect to time. And r is a variable. It's not the variable we're differentiating with respect to, though. So when I get to take the derivative of this thing, you're going to pretend like it's normal. So if you took the derivative of this, you just bring the 2 down like we always do, and you would write 2 pi r, because pi is just a constant. It's not actually a variable. Is that okay?
dr dt.
But then because this is not the variable I was differentiating with respect to, you have to write dr dt after it. So we took the derivative of this thing, we pretended like it was with respect to r. So we brought the 2 down and made it 2 pi r. But then because we were actually differentiating with respect to time, we needed to put dr dt at the end. Is that okay? Now here's the good news. Here's what I want. I want dA dt. You have a formula that says dA dt is equal to 2 times pi times the radius, and they're telling you use the radius is 10 at this moment. So instead of me putting r there, I'm going to put 10 there. Is that okay? And then it wants me to multiply by dr dt. And when we started this problem, I said, oh, we got dr dt. Dr dt is just 2, so you're going to plug in 2 there. So we're going to multiply those numbers out. 2 times 10 is 20, times 2 is 40. And then we still have a pi, so we're going to tag the pi onto the end of it. And then our units on this thing are going to be feet per second. So what this is saying is that as we make the radius bigger at 2 feet per second, the area is increasing at 40 pi feet per second. So the circle's getting bigger as your radius is getting bigger at that rate. How did we know to do the derivative with respect to time and all of that? Well, it had to do with it being a rate. As soon as I know that it's a rate, I know time is the other variable we're talking about. And it specifically said how fast is the area changing. That's why I wrote dA. So dA came from them saying area. dt came from them saying it was a rate. So I know that's weird when you first see it. So we got another one. We got a cylinder this time. I'm going to try and draw a cylinder. I'm not as good with cylinders. Okay. Got a cylinder. The radius of my cylinder is increasing at 3 inches per minute, and the height is decreasing at a rate of 4 inches per minute. How fast is the volume changing when the radius is 8 inches and the height is 5 inches? I know there's a lot of words in there, but I'm going to put down the things that they did tell me. They told me that the radius is increasing. So dr dt is equal to 3 inches per minute. They also told me that the height is decreasing.
So dH dt equals -4 inches of that.
Mm-hmm. And what I want, it says how fast is the volume changing. So I want dV dt, specifically when R is equal to 8 inches and H is equal to 5 inches. So because I want a dV dt, I need volume for a cylinder. You might not remember this one as well. Whenever we want a cylinder, we want the area of the base times the height of the thing. The area of the base on a cylinder is a circle, so it's going to be pi r squared, just like our last one. And then we always multiply it by how tall the thing is, so we just pop an h on there. That's my volume for the cylinder. So there's my height, there's my radius. And so if I want dV dt, I need to take the derivative with respect to time for this whole thing. Now, right here, this is my F and this is my G. I have a product rule happening here. Why is this pi part of this? Because pi is actually a constant, it's not a variable. So when I go to take the derivative of this thing, it'll be 2 pi r and then dr dt.
Times h.
Times just the g, so we just pop an h on there. And then we put a plus sign. And then the second time through it, we leave the f alone. So we're going to put pi r squared and then take the derivative of h with respect to t. So this will be dh dt. And you could put a 1 if you were like, oh, h, it would be 1. Yes, it is 1 dh dt. I just didn't write the 1 because it gets absorbed. As scary as that looks, we actually have everything we need to answer this question because I want dv dt. And that's supposed to equal 2 times pi times the radius, but they told us to use 8 for the radius. Times dr dt, we got that number at the beginning of the problem, that was 3. Times h, they told us to use 5. Plus pi times radius squared, they told us to use 8 for the radius. Times dh dt, we got that one at the beginning of the problem, that's -4. And so we have everything, we just have to now multiply those things out. So let's see, that'll be 40 times 3, 120 times 2 is 240 pi. Plus, oh, minus, because there's a minus on that 4. Minus, and then that'll be 16 times 4 is 64 times 4 is 256. So that comes out to be -16 pi. And our units on this one are,
oh geez, that's a lot of
inches cubed per minute.
So 16 times 15. Sorry, I'm confused.
Totally okay to use a calculator there if you need to.
Okay. That's just a lot of that. Inches cubed in that. Okay.
And why do I know it's inches cubed? Because they asked for a volume changing. And whenever we're talking about volumes, we're in cubic, whatever the units are. And so we were using inches. So it's cubic inches, inches cubed. So those first two are just using geometry formulas to get us through. We don't always get to stick with straight up geometry formulas through the whole problem. Sometimes we have to use kind of clever changes as we go. So let's look at the next one. We'll use some geometry formulas, and then we also have to switch something over because I can't just use the formula the way it's written to answer this question. So this one says, water is being poured into a conical tank. So that means it's a cone shape. It looks like a snow cone shape. And at this particular cone shape, we've got a radius of 3 feet and a height of 12 feet. So I'll draw my cone. So the height on this thing is 12, and my radius is 3. And we're pouring water into that cone at a rate of 3 feet cubed per minute. If I'm pouring water into a cone, are you cool with that being the volume of the water that's going in? So what they've actually given us here is dV dt is 3 feet cubed per minute. How fast is the water level rising at the instant the water is 6 feet deep? So we've got a scenario where the cone isn't completely filled yet. So we're going up to a certain height of 6 feet. And we've got, at that particular point, our radius is not the same radius as the 3 that's at the top, because we're not all the way at the top. So our height isn't 12 at this particular point, and our radius isn't 3 at that particular point. We're going to have to go find some of that information to help us answer this question. So when they say how fast is the water level rising, what they're asking you for is the height. So dH dt. And specifically, they want that when the height is 6 feet. How do I solve this? So volume for a cone may have been a while since you've seen this formula. That's volume is equal to 1/3 pi radius squared times the height. That's the volume of a cone.
And so we do DH.
So we actually have a little bit of a problem at the moment because when I go through this problem, I'm going to still have an R in here. But in terms of things that they gave me to plug in, I have a dV dt, a dH dt, and I have H is equal to 6, but I don't have any R's in here. So before I get going, I need to get rid of the R in this formula. And so in order to do that, I need to come up with kind of a tricky geometry scenario to write my R's in terms of H's because we do have H's. And so when we're looking at this cone at the top, the big cone, I didn't do a very good job of making a sideways cut of that cone. And then the littler cut down here, this would be like if I just drew a line straight up and down right here and just took half the cone. We can actually talk about these in terms of similar triangles. The big one, the height on this thing is 12 and the radius on this thing is a 3. And I don't know what the hypotenuse is, but I actually don't need it in order to solve this thing. On the smaller one, my height is just H and the radius is just R. And so I can write a proportion now that's going to let me write the R's in terms of H's. So what I'm going to do is I'll talk about the radii first. I'll say 3 gets matched up with the R. And then I'll talk about the heights. I'll say the 12 gets matched up with the H. There's a proportion for those things. You could have also said the 3 goes with the 12 and the R goes with the H and set them equal. The proportion will solve the same way. But if I want to get this so that I'm solving R in terms of H's, if you cross multiply this, you get 12R is equal to 3H. And then we can just divide both sides by 12. And that's going to give me R in terms of H.
R equals H over 4.
Oops. Or H over 4 is also fine. So what I'm going to do is where I see R in here, I'm going to go ahead and plug in that H over 4. So this 4 gets squared, so that's 16 times 3 gives us 48 down in the bottom. H squared times another H gives us H cubed. Why do we do that? Because ultimately I want to do a dV dt on this thing, but I want to have no R's in it. So I'm happy now. Now we're going to have just things that we actually can solve for. So now I'm going to go ahead and do derivative with respect to time. So dv dt is equal to, we'll go ahead and bring that 3 down. So it'll be 3 pi h squared over 48. But then dh dt, because we're taking the derivative of h with respect to t. So that simplifies a little bit. 3 over 48 is 1 over 16. So we can write that as pi h squared over 16 times dh dt if we want to make the numbers a little smaller. So with this particular formula, we have all these things now. dv dt is 3. So I'm going to plug in 3 for that side. On the other side, I have pi times h squared. They told us to plug in 6 for the h. 16 is still in the bottom. And then dh dt is the thing you're solving for, because it said find dh dt when h is equal to 6 feet. So this will become 36 pi over 16. dh dt. And then if you want to get dh dt by itself, we need to multiply both sides by the reciprocal of 36 pi over 16. So we're going to multiply by 16 over 36 pi on both sides.
Which is equal 1. Damn.
Would not equal 1. This part will, if that's what you meant. So 3 times 16 is 48 over 36, and 48 over 36 is 4/3. So we get 4/3. The pi still stays in the bottom, is equal to dh dt. Our units on that thing are feet per minute. So dh dt is 4 over 3 pi feet per minute. So sometimes we get lucky. So like our first few problems, we didn't have to substitute anything out. This third one, I had the formula, but I had an extra variable in there that I didn't get information for. So that was how I knew that I needed to do this separate piece here to try and substitute out R's in terms of H's. So that was why we did that step there. Then I had all the things I needed to plug in. Sometimes we don't have that kind of formula. So this next one isn't going to be quite as straightforward with like, what formula am I using? Because it's a scenario. So we have to think a little bit about what we do know about some of these distances. So it says at 8 a.m., Pam is 31 miles west of Jim. Okay. So I'll put Pam over here, and she's to the west of Jim. So that's her P, and then I'll put Jim over here and straight on over. Okay. Will be Jim, but then it says that Pam walks east at 4 miles per hour and Jim walks south at 5 miles per hour. So Jim is actually walking straight down, and so Jim ends up down here somewhere. Here's Jim. Pam is walking this direction. So I'm gonna put arrows kind of pointing the direction that Pam is walking. Jim is walking straight down. Find the rate at which the distance between them is changing at noon. So we started at 8 a.m. and so noon is 4 hours later. So we'll use t is equal to 4 in this problem.
Which way is east again?
East is over here and he's moving, sorry, west is over here, he's moving east. Pam's here, she's moving east. So distance between them, even though this point is moving forward like this, and this point is moving down here, the distance between them, do you agree that's the hypotenuse on a right triangle?
Yeah.
So we're talking about a hypotenuse that's changing. So I'm just going to choose kind of like a random place to draw that in. I'm just putting in a hypotenuse right here. Okay. That's not where the actual thing is. I'm just putting it in so that I can start labeling things. Pam is walking in our X direction, so I'm going to call her direction X. Jim is walking straight down, so he's walking in a Y direction. I'll call this side Y. And the side that's the distance between them, I'll call that Z. That's our hypotenuse. And so something that we can say about a right triangle is that the x squared value plus the y squared value is supposed to equal the z squared value. We do know that. And then they gave us a bunch of really weird other information that isn't quite as straightforward. So if Pam starts 31 miles away from Jim, and she's walking this way at 4 miles per hour, if we're talking about 4 hours, this was 31 feet originally, but she's getting closer and closer and closer to this point, right? So it's going to be 31, and what I'm actually going to write, I'm going to say that the x direction, which is the direction that Pam is walking, I'm going to say that that's equal to 31 minus 4 times t, because that's just however many hours. And then at 4 hours, yeah, that would be us subtracting 16 from it. In the y direction that Jim is walking at 5 miles per hour. So Jim started right here and ends up down here. He's doing 5 times however many hours he goes, right? So it would be 5 times t for him. Is that okay?
Instead of 31, because he's not west, he's not gone south. Oh.
So if we have to write a dx dt and a dy dt, we're actually looking at these two equations up here to write those things. So for dx dt, you're going to write, that's a constant, so that'll become a 0, right? We're going to write -4. My dy dt, it's just a +5. And they're miles per hour. I could put mph after them. So that's some information, but here's what's a little bit tricky here. So if I take the derivative of the equation that we've got, you're going to have 2x dx dt plus 2y dy dt is equal to 2z dz dt. And ultimately, they're saying find the rate at which the distance between them is changing. They're asking you for your dz dt because that's the distance between them. So we want dz dt. That's what we're solving for.
So our dx dt is.
And we're using when t is equal to 4. So looking at that formula, I have the dx dt, that's this. I have the dy dt, that's the 5. I am told to use when t is equal to 4, but there's no t in here. And so that's giving us the next hint about what we need to do. I have x, y, and z that I'm going to have to be able to plug things in for in order to solve this. So using that t, I need to go figure out what x, y, and z would need to equal. So what does that actually mean? Well, thinking about this equation right here, that x is equal to 31 minus 4 times t, we're plugging in 4 there for the t. So that's going to be 31 minus 16, which is 15. For the y, we have 5 times the t, so we're going to plug in our 4 there. So that's 20 miles. So I have the x and I have the y, but I don't have the z. But that's okay because I can go ahead and make myself a right triangle. My x is 15, my y is 20, and so I can use that information to go find what the z is supposed to equal with my Pythagorean theorem.
Which is 20 squared plus 15 squared equals z squared.
So we've got 625 is equal to z squared, so that means z is equal to 25. All right. So I have my x, it's 15. I have dx dt, that's -4. I have my y, that's 20. I have dy dt, that's 5. I have the z to plug in, that's 25. So the only thing I don't have is dz dt, which is what I was trying to solve for. So we have everything we need now. So 2 times our x is 15 times dx dt is -4. Plus 2 times our y is 5. Oh, sorry, our y was 20. There we go. And my dy dt is 5. Y is 20. Dy dt is 5. That's 2 times our z is 25 times dz dt. Cool. So 30 times -4 is -120. That's 40 times 5 plus 200 equals 50 dz dt. Okay, so we have
80 over 50.
Yep.
dz dt equals 8 over 5. Miles per hour.
And there you go. So learning the implicit differentiation stuff was mainly because when you go do related rates type problems, you have to be really comfortable with taking derivatives of different variables with respect to some other variable. In a lot of these, they're rates. And so whenever they're talking about a rate, it's going to be with respect to time. dt usually ends up being our bottom part on our derivative that we're going to set up. hopefully that was a helpful introduction, and then you'll see this in class on Wednesday, and it'll be a little less confusing when we go through it. The next parts of the class have a lot of stuff that involve putting things together that you've already learned. So it's not that it's all brand new, but if there were parts you don't understand from before, make sure you're coming to check in so we can get implicit differentiation down and that kind of stuff so you can understand how to do these types of problems. Good work, guys. I got office hours online tomorrow. If you just go to the Canvas page, you can find the link for Zoom if you want to see me. And the sign-in sheet is up here if you didn't get a chance to sign it.
So for dx dt, it will be dy dt.
They came from me taking the derivatives of these formulas up here. So if I just looked at that x and I said, hey, take the derivative of 31, sorry, 31 minus 4t. 31 would be 0 when we take the derivative of it. When you take the derivative of that, it would be -4. So that's where that -4 came from. And then when we take the derivative of dy dt, then it would be taking the derivative of 5t, which would just be the 5. That's where that one came from.
Okay, and then where'd you get both of these from?
So because Pam was 31 miles away at the start, but she's walking closer to that point, it's going to be 31 minus whatever the rate is times the number of hours. And so the 4 came from how fast she was walking and t came from the number of hours she was walking. Yeah. And then he was walking 5 miles per hour south. And so we do 5 times however many hours. That's where the 5t came from.
Okay.
That part's tricky.
All of these?
The trig ones, and really you only have to memorize the 3 of them.